Let's look at an example of how to use the displacement equation for a simple harmonic oscillator. So in this example, the time period of a simple harmonic oscillator is stated as 2.50 seconds. And the oscillator is released from a negative displacement of 0.3 meters at time equals 0. So when the clock starts, what will be the oscillator's displacement at the following times? Okay, so the first thing to think about is what actually will the graph look like for this oscillator, so that just roughly so we can figure out which equation to choose. Well, it says the oscillator is released from a negative displacement of 0.3 down here, so minus 0.3 in other words, at time equals 0. So we can see that that's going to do an oscillation like this, starting at minus 0.3 and then oscillating, assuming there's no friction or anything else, to plus 0.3 meters and backwards and forwards. So that means that we know that the amplitude of this oscillator is 0.3, is 0.30 meters. And because it can't go bigger, that's the maximum displacement if that's where it's released from. And we also know the time period is 2.5 seconds. And of course from that we can work out omega, which is kind of useful because omega is 2 pi over t. So if we calculate that, we find in our calculator, then we find that omega is 2.51 radians per second. So we're doing pretty good. We know amplitude and we know time period. And we also know the shape of the graph. And of course the shape of the graph is a minus cosine. So we can actually come up with the equation, because remember, x equals, if it's released from maximum negative displacement, is minus a cosine omega t. And we know the values of a and omega, so we can actually get an exact mathematical equation. X equals minus 0.30 times the cosine of 2.51 t. So how cool is that? So that is actually the equation we need to use to find the displacement absolutely anywhere at any time in the future, assuming nothing changes. So it's looking pretty powerful, so let's give it a go. Now remember that this angle, because omega is in radians per second, and it's radians per second times seconds, then that angle has to be in radians. So make sure your calculator is in radian mode. If it's a Casio, then that's shift mode, and then it gives you some options. Number 4 I think is, or my one anyway, is radians. So you've got to flick over to radians however you do that on your calc, and then we can have a go at these. So number one, time, we want to find the displacement at time equals 0.20 seconds. Well, we can kind of think, okay, well, it's not going to be very far through its cycle at that short time. But let's plug it in. So x equals minus 0.3 times the cosine of 2.51 times 0.2. So that's what goes in the calc. And if you do that, you should find that the displacement comes out as minus 0.26 meters, which seems pretty reasonable because it seems as if it will have just kind of got underway. So it won't be at its maximum negative displacement anymore, it'll be a little bit further along. Let's do the second one. So for the second one, we've got time equals 1.7. So pause the video and have a go at the next two, and then see if we get the same result. Okay, so at time 1.70 seconds, we just sub that into our general equation, which we've figured out, which is minus 0.30 cosine 2.51, which is omega, times 1.70, and that gives positive 0.13 meters. So that's our answer for number 2. And for number 3, now this is interesting. Well, it still works is the great thing. This is obviously more than one time period, but the beauty of a cyclical cosine or sine equation is that it doesn't matter. They repeat because the values repeat, as you can see from the graph. It just keeps repeating. So we can just plug it in, we can just do the same. So you just go 0.30 cosine 2.51 times 6.1. Cosine doesn't care, it's going to make the calculation for us. And if you plug that in, you get plus 0.28 meters. And that's our answer for part 3.